Okay, so we defined integration for positive measurable functions, and we looked at some properties monotonicity and things like that. We have to prove that the integral is linear in the sense that if I take two functions positive measurable functions f and g, then the integral of f plus g is the integral of f plus integral of g and things like that. So, if you notice the definition of the integration for simple functions, you will see that linearity is sort of built into it, but it is only for simple functions. From simple functions we will need to go to all positive functions by taking appropriate limits. So, that is what we will do, but first let us start with a simple proposition. So, I always have x script f and mu, x is a space, f is a sigma algebra of subsets of x, mu is a countably additive measure. Okay. So, let S be a positive measurable simple function. So, as of now we are defining integrals only for simple functions and then positive functions. We will extend it to real valued and complex valued functions later on. So, define, so we are taking one simple function s, define nu of a to be integral over a s d mu. So, recall that we have defined integral over a f d mu for any positive function to be equal to integral over x chi a f d mu, right. So, that makes sense. So, this is a positive number, okay. It can be 0, but it is a non-negative number. So, for each a in script f I am giving you a number, okay. Then nu is a measure. Okay. So, this is how you construct new measures out of old measures. So, if I have a countably additive measure mu, I can define another measure using a positive function. So, let us prove this. This is very useful and we will use it in the next theorem. So, to prove that, so recall what is a measure. So, to prove that nu is a measure, I need to show that two properties, nu phi is 0 and countable additivity, right. Union A j is summation nu A j, right. These are disjoint sets. There are two things to be done. So, let us look at the first one. What is nu of empty set? Well, this is integral over empty set s d mu. So, remember this is 0 because mu of the empty set is 0, right. This was one of the properties. So, let us go back and see that. So, even if this set has measure 0, then the integral is 0, whatever f is does not matter. That is the property we have used here. Because this set has measure 0, so integral will be 0. So, integrals over sets of measure 0 is 0. Second property, so I take a1, a2, a3 etc. disjoint. Disjoint measurable sets in script f, and then I want to show that. So, to show that nu of union A j, j equal to 1 to infinity equal to summation nu of A j, j equal to 1 to infinity, right. This is what we want to show to prove that this is a measure. So, let us start with that. So, remember s is a simple function, right. So, I can write it as, so let us write that s is a simple function. So, I can write s as, so s of x as summation j equal to 1 to n finite sum alpha j chi e j of x, right. I will assume that e j are disjoint, okay. I can always do that, this is without loss of generality. If they are not disjoint, you can make them disjoint. So, if I look at A, so A is union A j, j equal to 1 to infinity. I want to look at nu of a. What is nu of a? This is integral over a s d mu. This is the definition, which by our definition integral over the whole space. Now, I look at chi a times s d mu, okay. But s is our simple function. So, I have chi a times summation alpha j chi a j d mu. This is how it looks like. Now, comes an important property of indicator functions. If I multiply chi a with chi e j, this is nothing but chi of a intersection e j. Why is that? Chi a, remember chi a takes values 1 and 0. Chi a is 1 if x is in a, otherwise 0. So, when I multiply, if I want to get 1, x should be in both the sets a and e j. So, it should be in a intersection j. If it is outside a or outside e j, it is 0. So, the product is 0. So, that is simply the indicator function of a intersection e j. So, this tells me that this is equal to integral over x summation alpha j chi a intersection e j d mu, which is, now this is a simple function, I know how to integrate it. So, this is simply j equal to 1 to n alpha j mu of a intersection e j. Okay, so, we start from here, we start from the right hand side. This is equal to, so I am starting from here, this is equal to, remember a is the union of, sorry, a is the disjoint union of a k, right, k equal to 1 to infinity. So, I can plug in that here. So, this is simply union a k equal to 1 to infinity, but these are disjoint, right, e j's are also disjoint. Okay. So, this is simply j equal to 1 to n. Remember, mu is a countably additive measure, and when I intersect, so let's rewrite this. This is simply union k equal to 1 to infinity a k intersected with e j, right, that is how each term is. So, this is simply union of k equal to 1 to infinity a k intersection e j, and this is a disjoint union, right, and mu of that would be the sum of things, right. So, mu of that would be k equal to 1 to infinity mu of a k intersection a k intersected with e j. So, I have a finite sum here and an infinite sum here, I can interchange, this is finite. So, this is simply k equal to 1 to infinity summation j equal to 1 to n mu of a k intersection e j, which is equal to summation k equal to 1 to infinity. Well, what will be this? This is simply integral over x chi a k times summation j equal to 1 to n. Sorry, there is an alpha j missing. So, there is an alpha j here, there is an alpha j here. So, alpha j mu e j, right, indicator of e j, indicator of e j d mu, right, exactly like this, exactly like the earlier step. But now I have a k here and x here and I am integrating against mu. So, that is integral over a k, right, that is the definition, k equal to 1 to infinity integral over a k s d mu, right. Remember, this is my simple function s, but this by definition is the value of nu of a k. So, I started with A is to be the disjoint union and nu of A is equal to summation nu A k. So, that proves that nu is a measure, right. So, this is done. So, this is why it is a countably additive measure. Okay, so, let us use this to prove linearity of integral, but as of now we will do it only for simple functions. Okay. So, let us write this as a theorem. So, I have x f mu usual triple, x is a space, f is a sigma algebra of subsets of x, mu is a countably additive measure. Okay. So, if S and T are non-negative simple functions, then integral over x s plus t d mu equal to integral over x s d mu plus integral over x t times g mu. So, remember all these things are well defined now. If s is simple, t simple function, then I know s plus t is also simple, right. So, the left hand side is well defined. If I write this as summation alpha j chi e j, I know what the value on the left hand side is. Similarly, I know what the values on the right hand side is. So, this proves that it is linear for simple functions. Remember, multiplying by a constant, if it is a positive constant, because we are right now looking at only non-negative simple functions. If I multiply it as a positive constant, that comes out, that we have already seen, that is one of the properties we wrote down immediately after the definition of the integral. So, let us prove this. So, we start with S summation j equal to 1 to n alpha j chi e j. So, I will assume that e j are disjoint. So, remember that this we can always do. I can also assume that union e j is the whole space. Okay. Why is that? Well, so let us say this is my space X, and let us say this is E1 and this is E2, E1 disjoint, right. So, E1 and E2, and my simple function is chi E1 plus chi E2. There may be constants, but let us look at this example. So, here E1 union E2 is not the whole space, but I can always do plus 0 times chi E complement, right. E1 union E2, let us call this E3, which is the complement. So, I will call this E3, right. Well, that is how it is, right. So, if it is, it is 1 here, it is 1 here, and E3 does not exist. So, the simple function is 0 here. So, if E3 is not present in the expression for simple function, I can always multiply by 0 and add chi E3. So, that this I can always do. So, that means there is probably a set where the simple function takes the value 0. Similarly, I can write t equal to integral summation j equal to 1 to m some other number beta j, let us call it beta k chi f k. Okay. So, f k, so I will write k here, f k disjoint and union f k, k equal to 1 to m is the whole space X. Now, I want to say that if I integrate s plus t, these two, sum of these two functions, sum of s and t, then I am going to get the sum of the integrals of s and t. So, for that we will use the earlier result. Okay. So, let us look at the picture again just to get some idea. So, this is my space X and I have disjointified to get me E1, E2, E3 and so forth, E4 let us say. That gives me the simple function S. But for simple function T, I may have a different disjointification, right. So, I will have F1, F2, F3 and so on. So, if I intersect both of them, so this would be intersection of let us say E 3 and F 2, right. So, this is E 3 intersected with F 2. So, if I look at all such pieces, that is a disjointification of x. So, the whole x can be written as EI or EJ intersection Fk, right, union j equal to 1 to n, k equal to 1 to m, right, that is how it is, and this is a disjoint union. Okay. So, let us call this AJK. So, I can write AJK equal to EJ intersection Fk. Okay. Now, integral over AJK of S plus T d mu. Well, what is this? This I know by definition is indicator of AJK, you multiply that with S plus T d mu, which is nothing but, well, what is AJK? AJK would be one piece like this, right. On AJK, so remember AJK is nothing but EJ intersection Fk, S takes the value alpha j, T takes the value beta k, right, that is how it is defined. So, S plus T takes the value alpha j plus beta k. So, S plus T is the simple function which takes the value alpha j plus beta k in each AJK. So, this is equal to alpha j plus beta k on AJK. So, its integral is nothing but alpha j plus beta k into the measure of AJK, right. That is how the integral for simple functions is defined, which is nothing but I can distribute this mu of AJK plus beta k mu of AJK, which again by definition is simply integral over AJK. Alpha j is simply the value of S on that set. So, this is just S d mu plus integral over AJK T d mu. Okay. So, by disjointifying into smaller pieces, we have been able to prove that on AJK we have linearity, right. Then we sum up. Okay. So, let us see. So, now consider summation I comma j integral over, okay, so maybe let us use j and k, j comma k over AJK of S plus T d mu. Well, this is equal to, recall the previous result, if I have a simple function, if h from x to 0 infinity is simple, then nu of a equal to integral over a h d mu is a measure. This is what we proved previously, right. So, this is the previous theorem. So, we have a similar situation here, right. This is, consider this as my h, then this is a measure. So, I can think of this as nu AJK, right, but AJK are disjoint. So, this would be integral over union AJK of S plus T d mu, right. Why is that? Because AJK are disjoint, AJK are disjoint and nu is a measure, right, we use this. So, it will be nu of union AJK, right. So, this is nothing but nu of union AJK. Okay. Well, union AJK is the whole space x S plus T d mu. right. Let us go back to AJKs, then we will see that. Yeah. So, these pieces are AJKs, right, and if I put together all of them I will get the whole space X. Okay. But let us look at, so this is one end. So, let us look at LHS. So, this is equal to, I know at the level of AJK I have linearity, right. So, if I integrate over AJK I know that it is the sum of two things. So, this I can write as j comma k integral over AJK S d mu plus summation j over k integral over AJK T d mu, right, because this splits into two things and the summation splits it into two things. But now I can use the same property again, use the same previous theorem that the integral is a measure. So, here this is like nu or some other measure, right, with respect to the simple function S. So, take h as S, then you see that this is a measure and AJK are disjoint. So, you are summing the measure of AJK. So, this will be equal to integral of union AJK S d mu plus integral union AJK T d mu, right, which is same as. So, remember union AJK is the whole space S d mu plus integral x T d. Okay. So, what we have proved is this is equal to the sum of these things. So, integral is linear when we are looking at simple functions. Okay, so, we conclude this lecture. Just to recall, we started with positive measurable functions, and well, we initially defined integration for positive simple functions. That was a natural extension of whatever we have seen for step functions in the case of Riemann integration, but now we allow much more general sets. So, that is how the simple functions came into existence and the integral of positive simple functions were defined, and using that for any positive measurable function we can define the integral to be the supremum of the corresponding integrals of simple functions which are less than or equal to that particular positive measurable function. And we saw some properties, monotonicity and how the positive constants come out, and now we have proved that it is linear with respect to simple functions. So, if I take two positive simple functions, add them and integrate, that is same as the sum of the integrals of the positive of the individual simple functions. Well, we have to extend it to all positive functions, but that will be done in the classes in the future. Okay.